J.J. Thomson, he discovered electrons. When he discovered electrons, at that time that we didn't have a proper understanding of what atom was. John Dalton was another scientist who came up with the idea that materials, matter, consist of atoms, and atoms are basically they come in different shapes and different masses depending on the different types of materials. And he said that when you look at a compound, it consists of different atoms that have got different properties. So we didn't know what was inside. Thomson came up with a plum pudding model. So he basically, it's just like cupcake. You have a cupcake, and in that cupcake, you have got these little chocolate chips. So it's just like plums in plum pudding. So he discovered electrons and he found out they have got negative charge, and he gave this model, plum pudding model, where that negative charge is like the plums. And because the atom has to be neutral, so he thought that the rest of the pudding is positive charge distributed equally. So that's his Thomson's model. At least he came up with the model discovering another negative particle. So this experiment is about finding the charge to mass ratio. And let's look at how he did that. So at that time, when J.J. Thomson was doing this experiment, this cathode ray tube is quite popular. Cathode ray tubes are basically an evacuated tube where you have air at a very low pressure, and that tube has got two electrodes, and then you apply a high voltage to this thing. So what would happen is that from this cathode, electrons, or at that time they thought it's a ray. They didn't know what it was. They actually thought it was atoms or some other molecules, and they also thought it could be some kind of electromagnetic wave because it had rays properties. So this is the kind of thing that J.J. Thomson used to do his experiment. So in his experiment, he had this tube into two compartments. So one is for the evacuated tube, where you have got a cathode and anode, and then he extended to another compartment like that. And here it's a fluorescent screen, because at the time they knew that the cathode rays, when they come and had exposed to a fluorescent screen, it emitted light. So this is cathode and this is anode, and he connected a power supply here. So this is going to be, and that produced the cathode rays going straight up here. But they were going on straight lines, that they observed that before. And now what he did was he applied an electric field by placing these positive and negative plates. So this is positively charged, the one at the top. So this is positive and this is negative. Why did he do that? He wants to find out he can deflect it. Actually, before this experiment, he tried it and he was able to deflect the light using the electric field. But in this experiment, he used both electric and magnetic field. So to create the magnetic field, he had this coil, a circular coil, and he applied a voltage, and that produced a current, which in result create a magnetic field. In this case, it's going in. So first, he just turned on the current to these electrodes, these two positively and negatively charged plates, which created a the electric field that deflected this light this way, because it went this way. So he did that, number one. And then he applied the magnetic field which deflected light this way. Two. And then he tried to adjust the voltage and brought the ray to the middle part where there is no deflection. So first by the electric field deflecting up, and then with the magnetic field deflecting down too, and then he got to the neutral place. So from that's the breakthrough. From that he was able to find the speed of this cathode ray, the speed of the cathode ray, which at the time they considered it as an electromagnetic wave. They also knew that electromagnetic waves travels at the speed of light. If the magnetic field due to this coil is B, and the electric field due to these charge plates are E, and assume the velocity of this ray is V. So at a balanced position here, where we are neutralizing that the upward and the downward forces, one is upward due to the electric field and the downward due to the magnetic field. So say this is FE and FB. So FE is given by EQ. E is the strength of the electric field and Q is a charge. We can also say E is equal to V over D. So voltage divided by the distance. Voltage is the applied voltage between these two plates, and the distance between those two plates is D, and that gives an indication what the E is. Now the force due to the magnetic field, we can say FB, because B is the magnetic field, is given by BQV sine theta, but here the theta is 90 degrees, so we can say BQV. So at this position where we have got both forces equal, so that the ray is going this way, because the ray goes directly at two instances. One, there's no fields applied, no electric field, no magnetic field, and then it goes directly. Or if both forces are equal, then it'll go this way. So now we're going to equate those two forces. So FE is equal to FB. So that means EQ is equal to BQV. So we can cancel Q and Q here. So that means V is equal to E over B. So Thomson and other scientists were able to find the speed of this cathode ray that they thought it's an electromagnetic wave, and they found out that E, electric field, obviously they find from here, and the B also they can find from this coil. They know the applied voltage and the number of coils and the type of materials. They found the magnetic field strength, and they found the velocity. And the velocity they found, the speed they found, is much, much less than the speed of light. So that concluded that electron, or this cathode ray, was not an electromagnetic wave. It's not light. So that's one thing. And also they knew that they were able to deflect these through electric field, and so they know that it's going to be a negative charge particle. Now the second part of the experiment was, because initially that there was a neutral, there no fields were applied, and then he applied these electric and magnetic field and brought that line to a neutral position where the forces are equal. And then what he did was he removed the electric field while having the same voltage, and the speed of the the ray was the same. So he didn't change the velocity, he didn't change the electric field, he changed the magnetic field with the same variables. He just removed the electric field. So what would happen? That you only had this one, only the deflection due to the magnetic field. So when it deflects, there's a radius because it's going to be like a circular motion. Because when the cathode rays, that's what they thought the other day, when these negative particles, negative rays, are going at a velocity v, is going through a magnetic field, that goes through a circular motion because the force is perpendicular to this arc. So it goes through a circular motion. So analyzing that circular motion and the force that is applied due to the magnetic field, he was able to come up with this equation. That is, so it is a circular motion. That means FP is equal to mv square over r. So v is the speed, r is the radius of that arc. So FP is equal to PQV is equal to mb square over r. And now from here you will cancel this v and another v. So we will get the Q over M. I mean, that's the whole objective of the experiment, is to find out the charge mass ratio. So you get B over RB. So this is V. But we know V is E over B. So that's going to be equal to E over, that's going to be E over RB squared. So what were the conclusion from this experiment? One is that obviously he found out these are negative because they were deflected towards the positive side of the plate. So they were negative. And also there were particles. One is that you can't deflect electromagnetic waves using an electric field. So that shows it's a particle. And QM, which is a ratio between the charge mass, obviously shows that the particle has a mass, and the electromagnetic wave, they don't have a mass. So this experiment basically ended the debate over what these cathode rays were. I mean, people thought it was atoms and molecules and gas particles or electromagnetic waves, and now they knew it was the charged particle which is negatively charged, and Thomson finally concluded it was part of an atom.